In this video, we're going to continue our study of the transfer function Laplace transforms for differential equations, and we're going to focus on the initial conditions and control aspects of the transforms. So just a reminder that when you're looking at Laplace transforms, we typically do not use the definition unless we have to. What we do is we simply look up on a table some pre-computed values for this transform. And what we saw earlier was that when we looked at a first order system like a heating cooling system with a control, we ended up with our transfer function times something to do with the control plus the initial conditions. And exactly the same thing happened when we looked at a second order system. We ended up with the control plus some additional terms due to the initial conditions. Now the question I've always asked myself when I look at videos online about all of these calculations, with specifically about transfer functions, these initial conditions are almost never in the equation. And there's a simple answer for that, which is most of the time the control is what we're most interested in. And in some sense, if we're interested in a graph of against time here, what we care about is the long-term behavior. Does some system converge to a temperature I care about? And the initial conditions don't really play that much of a role, in which case maybe we assume they're zero. In other words, if these guys were all assumed to be zero, they wouldn't show up in the math. And that's okay up to a point, but if you're actually going to simulate things, assuming that your system always has to start at zero seems a little presumptuous. So here's another way to look at it where it seems maybe less dodgy and I think is a better story for why we end up focusing only on the control and not so much on the initial conditions. And here's the reason. We can take the initial condition and put it inside the control if we want to. How would that work? Well, if you take a quick look at the table of transforms back here, there's an interesting function called the delta function. Now, the delta function is an engineering construction. Mathematicians, one trick that every mathematician hates is it is a function that has unit area, so it has exactly area 1, but that isn't good enough for it, engineers. What they did is they took that area 1 and they squished it. So they squished it so it's taller and narrower. And then they squished it again so that it became super tall and super narrow, but always with area 1. And so this, if you do it in a limit, you get this spike function, which is delta of t. And this is a surprisingly useful tool. It's basically like, or it's the analogy people use in control theory for this delta function is like hammering your system literally with a hammer. You're giving it a whack. So you spike up and come down. The area being 1 lets you pretend that this is a little more under control mathematically than it probably is, but it turns out to be an incredibly useful tool. The delta t minus a that you see in the typical Laplace transform function sheet is just the acknowledgement that you might want to have it on at some other time. So if you turn it on at time a, then you'd use the delta function at t minus a, which is a right shift by a. If you go back to your grade 11, grade 12 calculus functions, same height, area 1, all that, just move to a different location. And the idea, especially in a lot of mechanical systems, is that you might have some kind of jarring to the system, some kind of disturbance, and a delta function can help capture that. For our perspective today, though, the more interesting part is that if we do delta of t and look this up in our chart, if the a is 0, that's because it's not here, it's like minus 0, then the transform of it is e to the negative 0s, which is much better known as just 1. E to the 0 is always 1. Well, if we take a look back here, we could treat this as, or replace it with, the Laplace of a delta function times x naught. This would do the same job because it would give us 1 times x naught in the transform space. So how does this help us think about our initial conditions? Well, we could just choose our u to be equal to 1 times x naught, and that would mean treating our original time-based control as having a little spike of magnitude x naught at the beginning. So we whack our system with an x naught scale hammer, and then we add on whatever else we want. and then we don't need the initial conditions anymore. So the argument is, if we mathematically here need initial conditions, we can take care of it in other ways. We can take care of it by adding a delta function, a little hit to the system right at the beginning with magnitude x naught, and that would do the same thing as removing the initial conditions and just putting it all in the control. And we can do something very similar here, where we take all of these terms and we would just have our choice of u of s equals to, again, we just want 1 times m x prime naught, the velocity, and our initial position. So the actual control we would apply would be a delta function at the beginning times the magnitudes. These are all just constants. So times the magnitudes of these things. So we could hit the system with a delta function here and get the result that we want. It's a little trickier for this, but we can also do it in another similar way. And again, the bonus of that, the goal of that, the outcome of that, is that all of this can get put inside the U. If we need to handle initial conditions, we can handle them in the relatively rare instances where it's crucial by just modifying our control function. And then after that, we can add whatever other terms we need to actually do the control that we want, but we factored out the initial conditions. We have a way to handle them that means we don't need to drag them through all the analysis that we do later on. If we have initial conditions that are critical, we can put them in the U if we want to, and then proceed as if all the initial conditions were 0, and we just tweaked our control function. The reason that's nice is that it means we can boil our systems down to this form here. Notice this is much simpler. It's just our transfer function times our control. Transfer function times our control. So, next observation. Why do we care about transfer functions at all? If we focus on this, or we focus on this, and call them the transfer functions here, if we take a look at the table that we had a little while ago, let's focus on this one first. This is 1 over s plus k. If you scroll down to here, you see, oh, there's one s minus a. That's an awful lot like s minus k. If we go back to the kinds of functions that would give rise to that, it'll be an exponential. And if we do the signs right, this would get converted to, through an inverse Laplace, this would get converted to an exponential e to the negative kt. Well, that's no shock whatsoever for a temperature model. In fact, we know that that would demonstrate a decay at a rate defined by the k value. And that exponential decay somehow characterizes the natural behavior of the system. If you look at the transfer function and you memorize the sort of core rules that are in that left-hand column here, looking at this left-hand column for most of the cases, we can then interpret that as a natural behavior that we're going to see in the system. So if I have a transfer function that's 1 over s plus k, I can do a quick little math and recognize that the time domain, time against x here, is naturally going to be an exponential decay. If we look over here, we see a quadratic, and not too surprisingly, if we go back to our pages up here, you see quadratics are associated with cosine sines. Now, not quite just cosine sines. If we were in a different kind of differential equation class, we would go through all the gritty details here. But for us, it's enough to note that if we have a quadratic and we had it as an ugly quadratic here, like s squared plus 2s plus 5 or something, it's going to be some combination of an exponential and a sine and a cosine in most cases. So this is going to lead to an e to the minus something t. Let's call it, we haven't used a, so at, cos of bt, and an e to the minus at sine of bt, because of the quadratic form down here in the transfer function, and the fact that those quadratic forms turn into cosines and sines or variance on them, with one little caveat. If you remember this physical system and how it behaves, it's possible to dial up the damping high enough that you get just pure exponential decays, like it's just so sluggish. That would happen if we could factor out linear factors, or factor linear terms out of that. So it was like 1 over s minus a1, and 1 over s minus a2. If we had two real roots here, that would lead to, in a manner similar to this, to exponentials, pure exponentials with no sines or cosines. So if we have a quadratic denominator here, if we can get it to, I should emphasize here, real linear terms, then we're going to get two exponentials by themselves. If we can't do that, then we're going to get some combination of coses and sines with exponential terms. And again, that captures perfectly the kind of oscillations that we'd expect to see in this kind of system. We'd expect to see oscillations that die over time, and an exponential times a sine and cosine gives us exactly that decaying oscillation form. Now, the key word you're going to see, whatever you look at control theory or transfer functions, is the word poles. So the pole is simply equal to a 0 or a root of the denominator. So we just focus on this part here, and if we look at the roots, let's actually do it in a linear face here. This has a root at s equals minus k. That is the pole. Here, we'd have to do some math depending on the m and c and k values. We'll illustrate that with some Python in a later video, but the idea is we could find the roots of this. That'll give us what we call the poles of the transfer function, and then depending on what those poles are, we know what kind of solution we're going to get. So when we get the transfer function, we can quite easily get a form for the natural behavior of the system. The unforced is another way to say it, unforced behavior of the system. And it all depends on where the poles are in your transfer function. Those contain all the information you need to predict what the natural behavior of the system would be, and then you can see what the consequence is of adding control on top of that. So specifically, how is the control related to, or how does it influence the final behavior? So this is the observed behavior, transformed of course, but that's what it is. This is our transfer function, and this is our control. Again, the b is part of that control. It's the scaling factor between whatever we can actually manipulate times some scaling factor to get it into the units of here temperature and here force. So the behavior in the Laplace domain is equal to a product, but just like when we saw with Fourier transforms, if you have a product in the Fourier transform domain or the frequency domain or the Laplace domain as well, since it's a variant on the Fourier transform, the behavior in the time domain is going to equal the natural behavior, which is defined by the transfer function, convolved with that big star here, asterisk, convolved with the control signal. So if we have the transfer function and we know what our control is, we can predict, we know, in fact, that the behavior that we see is going to be a combination of those two things, but not one we can necessarily intuitively leap to without some practice. But it is going to be the convolution of the natural behavior, which here would be our exponential decay. So our natural behavior for this system is just decaying. And then the control signal convolved with that, that's control signal is up to us, but we can predict what the behavior is going to be through that convolution. The same thing is true over here, except our natural behavior would be that decaying exponential, assuming the appropriate mass, damping, and spring constants. So whatever control we're going to apply, somehow it's going to get combined with this natural oscillations to produce the behavior that we actually see in the system. And this idea that the convolution of some natural behavior with the control signal is there for any linear system. Anytime we have a bunch of derivatives of some unknown function we're trying to track down, representing our behavior, and we have some kind of control applied to that, we're always going to end up with this mathematical form. And so we can always think of separating the output, the things that we're going to actually see, as some combination, specifically a convolution, of the natural system behavior and the control signal. And so that's going to be the deep insight we get out of the Laplace domain, out of the transfer function representation, that we wouldn't necessarily see with the state space system. Next up is going to be looking at simple U's of S's, simple controls, and seeing how they can help us to look at a system maybe without knowing what the transfer function is, but just knowing conceptually that it's there. So that'll be coming up next with step functions and impulse functions.